Jai Hind everyone. Myself Dr. Vanna Sharma from Ajay Kumar Garg Engineering College. My subject is Engineering Physics. Subject code is KS101T. The topic which I have started, that is wave optics. And in wave optics we have two topics in our syllabus. One is interference and the other one is diffraction. We have already completed all the parts of interference, and in diffraction we have discussed about the various topics like what is single slit diffraction, what is double slit diffraction, what is n slit diffraction. We have already discussed about these different type of diffraction patterns in detail in our last lectures. The topic for today's discussion, the topic which today I am taking, that what is the maximum possible order in a grating or in a n slit arrangement, what are the maximum possible orders which can be observed, and what are those orders which are missing in a spectrum in a diffraction grating. So we are going to discuss these topics, and after that we will discuss that what is the dispersive power of a grating. So these are the topics for today's discussion. These are the textbooks and reference books which you can opt for in order to study this topic of diffraction. That is a textbook of optics by Ajoy Ghatak, optics by Brijlal and Subramaniam, a textbook of engineering physics by Navneet Gupta, engineering physics by S.K. Gupta and S.L. Gupta. These are the various topics which we are covering under diffraction. So we have already discussed about this introduction of diffraction, then Fraunhofer and Fresnel diffraction, then a resultant of n simple harmonic motions. We have already discussed about this. We have discussed about single slit, double slit and n slit diffraction, which is also known as diffraction in a plane transmission grating. Now the topic for today's discussion, that is in a plane transmission grating in a n slit arrangement, what are the maximum possible orders which can be observed, what are the missing orders, what is the dispersive power, what is the resolving power of grating. So again in today's topic we are going to discuss about plane transmission grating, or you can say a diffraction grating. So the first one I am taking here, the condition for missing spectra, or you can say absent spectra. So as we have discussed about the diffraction pattern in case of plane transmission grating, and we have derived different conditions for maximas, for minimas and secondary maximas. And we know there is a famous equation for principal maximas in plane transmission grating or diffraction grating, and that equation is known as our grating equation. So you can see the equation number 1 which is mentioned over here. This particular equation is known as our grating equation. So according to the grating equation, you have E plus D sine theta equals to n lambda. As you can see in this equation, this E that in case of plane transmission grating or a diffraction grating, we are having n number of slits and every slit is of equal bit. So E is the bit of that particular slit. Every slit is of equal bit. So E, you can say that is the bit of the slits here. And D, that is the spacing between successive slits. So we have already discussed about this. So E represents the transparent part or bit of the slit. D represents the opaque part, or you can say that represents the spacing between two successive slits. So this equation number 1, it represents your grating equation. You can see this grating equation, it also represents the condition of nth order principal maxima. Means with the help of this equation, you can tell us that at what point you are going to get your nth order principal maxima. And there is one more interesting point there, that in case of n slit arrangement, just give me 1 minute. In case of n slit arrangement, basically we are having this r dash equals to r into sine n beta upon sine beta. If you remember, then this is the expression for resultant intensity in a plane transmission grating. If you will see this carefully, then the first factor, this R, it is because of, this is the contribution of a single slit, whereas the second factor, it is a contribution of n slit. Means the combination of these two, that is going to give you the resultant in a diffraction grating. Now, in order to find this absent spectra or missing spectra, meaning of absent spectra or missing spectra is that in a diffraction grating, you will see different order of maximas. You can see you will see your first order maxima, second order, third order, fourth order. But there will be certain order maximas which can be missing from that spectra. Now the question arises, what are those missing order spectra, and what is the condition under which we can decide that which order spectra will be missing from the spectrum? So in order to decide that, you are having this expression for resultant intensity. As you can see here, that R dash is the combination of these two factors. Now this factor, that is the contribution of n slit, whereas the first factor, that is the contribution of single slit. Suppose this second factor, it is giving you maxima, means because of the sine n beta upon sine beta, we are getting the condition of maxima. This factor is saying that you are getting your maximum intensity, and you know the condition of maxima for any nth order maxima. This equation number 1 represents the condition for that maxima. So you can see from equation number 1 that you are observing your nth order maxima at theta angle of diffraction. And the first factor, that is the contribution of single slit. This factor is giving you maxima, and you know its maximum value will be capital N. But if the first factor, which is the contribution of single slit, if that factor is giving you minima at the same point, then the resultant will be equal to 0. It means in that case, that particular nth order maxima, due to which you were getting this condition number 1, that nth order maxima will be missing. Or in other words, I can say like this, if this is giving you maxima, maximum intensity, but this particular factor is giving you minima, means 0 intensity, then what will be the resultant? Resultant will be 0. So if the nth order maxima due to this factor is observed at same point as the mth order minima of the first factor, then that nth order maxima will be missing from the grating, from the spectra. So you can see the nth order maxima from equation number 1 is observed at theta angle of diffraction. And you know, for single slit, the condition for minima is E sine theta is equal to m lambda. This represents the condition of minima. So if you are observing your minima at same angle of diffraction, means that nth order maxima is overlapping with the mth order minima of single slit. It means you are getting the minima due to first factor at same angle of diffraction, that is theta. So under this condition, this nth order maxima will be missing. So using these two conditions, that is 1 and 2, you can find that which order will be missing from the spectra. So if you will divide this equation number 1 with 2, you are getting E plus D upon E is equal to N upon M. So from here, if you want to write an expression for missing order, it will be your E plus D upon E into M. And you know this, in case of single slit, M can take all the integers values except 0, means M can take values 1, 2, 3, 4 and so on. So using this formula, you can find the absent spectra, or you can say missing spectra in a grating. So we are taking a few examples here. Suppose for your grating, this E is equal to D, means that width of the transparent part is exactly equal to width of the opaque part. So if you are taking this E equals to D, then this will be 2E upon E will get cancelled, and N will be equal to 2M. And you know, M can take different values starting from 1 to 1 and so on. So it means what orders can be missing from the spectra. So the orders which can be missing from the spectra in this particular case, those orders are second, fourth, sixth and so on. So for such type of grating where the width of transparent part is equal to width of the opaque part, for that type of grating, second, fourth, sixth, these orders will be missing from the spectra. The reason is very much, the reason should be clear to you. The reason is that the second, fourth, sixth, all these even orders, their maximas are overlapping with the minimas of single slit. So if the maxima is observed at theta angle due to n slit, and if the minima of single slit is also observed at same angle, then that particular nth order maxima will be missing from the spectrum. So this formula gives us the expression for missing order spectra in a grating. So I hope this is clear to you. You can take some more examples for this missing order spectra. If I am saying let D is equal to 2E. So if your width of the opaque part is equal to twice of width of transparent part, then this will be 2E. In that case, this is 3e upon e means 3m. So now you can easily understand that third, 6th, 9th, all the multiples of 3, all those orders will be missing from the spectra. So this is missing order spectra in a grating. Now the next question arises that what are the maximum possible orders which you can get in a diffraction grating. You know that in case of single slit diffraction, you are having one principal maxima which is having maximum intensity, then you are getting some secondary maximas and so on. In case of n slit diffraction, we are having large number of maximas, principal maximas. Now the question arises that what are the maximum possible order which you can get from a diffraction grating or in a plane transmission grating. So again, in order to get that condition for maximum possible order, we are using the condition of nth order maxima. So you know, in case of plane transmission grating, again that famous grating equation that will represent the condition for a principal maxima. So this equation, E plus D sine theta is equal to n lambda. This is your grating equation. You can see in this equation that this n, if you want to find the order, then order will be equal to E plus D sine theta by lambda. So if you will see this expression very carefully, then for a fixed light source, if the light source is fixed, it means this particular wavelength is constant, that is fixed. And for a particular grating, you know that width of the slit and width of the opaque part, that is also fixed. It means that grating element, which is this E plus D, that is also fixed. Means for a for a particular grating, for a certain wavelength, this order n, it is depending upon this factor sine theta. Means n will be maximum if sine theta will take its maximum value, because only the variable factor, only the factor which can change this order, that is your sine theta here. So depending upon the value of theta, your n, that you can decide at which point this n will be maximum. So you can see from this expression that n will be maximum for a particular grating and for a certain wavelength if sine theta is taking its maximum value. And you know the maximum value for sine theta is 1. So for maxima, if this sine theta is 1 or theta is 90 degree, then maximum possible order, the formula will become E plus D by lambda. So this is the expression for maximum possible order. So in a diffraction grating, or you can say in a plane transmission grating, by using the features of that grating, the features of grating means by that grating element and with the help of wavelength of light source, you can decide that what is the maximum possible order for that grating. So this example is taken over here. Suppose the grating element of a grating which you are using to get this diffraction pattern, if that grating element that is lesser than twice of the wavelength of light which you are using, so if E plus D is less than 2 lambda, then it is very much clear from here that this E plus D is having a value less than 2 lambda. It means the maximum possible order for such type of grating is 1, because now n max will be less than 2. So if n max is less than 2, it means the maximum possible order is 1. So only the first order spectrum will be observed for this type of grating. I hope now it is clear to you. You can take one more example here. So I am taking one more example here. Suppose this grating element, it lies between lambda and 3 lambda. So if it is between lambda and 3 lambda, and you have to decide that what is the maximum possible order for such type of grating. So you can see that this E plus D is less than 3 lambda. It means that maximum possible order will be less than 3. So in that case, the maximum possible order is your 3. So this is the expression for maximum possible order in a diffraction grating. I hope this maximum possible order and missing order is clear to you. Now the next one, that what are the applications of this diffraction pattern of n slit arrangement, or what is the application of this? So the application is, we can measure the wavelength of light with the help of plane transmission grating. So if a plane transmission grating is given to you, with the help of that grating you can find the wavelength of light. So you know, according to the grating equation, E plus D sine theta is equal to N lambda. You are going to perform an experiment in your lab, which is totally based upon this information or this plane transmission grating here. You have an experiment here. In which a mercury lamp is given to you, means that is a source of white light. So a source of white light will be given to you, and with the help of this phenomena of diffraction, you have to find that what is the wavelength of different colors which you are going to see through that grating. So you have to find the wavelength of those colors here. So that is the application of this plane transmission grating. And there is a very important point here, that if you want to study the diffraction of any light source, suppose you have a light source and the light source is having a particular wavelength, let it is wavelength is 5500 angstrom. So in that case, only that particular grating can observe the diffraction pattern for such type of light source, in which the specification of that grating is of the order of wavelength of light source. So that you have to remember, that the dimension of the grating and the wavelength of light source both should be comparable to each other. Only then you can get a diffraction pattern. So what you have here, you have this grating equation E plus D sine theta equals to N lambda. So if you want to find the wavelength using this particular expression, then the wavelength will be E plus D sine theta is equal to N. So this is the formula which is used to find the wavelength using a plane transmission grating. So suppose you have a mercury lamp or a white light source, then that white light source will give you different colors. And you know from this expression that for a fixed order, suppose I am taking only first order or second order, then N is fixed, and the grating specification is also fixed. It means E plus D is also fixed or constant. Then this angle of diffraction, it depends upon the wavelength of light source. So for different colors, you will get different angle of diffraction. That color which is having minimum wavelength, that the angle of diffraction for that color will be minimum, and the color which is having maximum wavelength in the spectrum, that color will be diffracted maximum, means the angle of diffraction will be maximum for that color. That is the reason when you are seeing a spectrum of white light, or suppose you have a white light source, then you will get that entire spectrum, you will get that Vibgyor pattern, and in that pattern the color which is having minimum wavelength, that will be diffracted least, and the color which is having maximum wavelength, that will be diffracted most. So in this way, using this particular expression, you can find the wavelength of light. So what you have to do, for a particular order of spectrum, you have to find the angle of diffraction. Once you will find the angle of diffraction, you will get the wavelength of light, right? So this is how you are going to find the wavelength using this diffraction grating. Next one is, we can find the value of this grating element. So determination of grating element, the number of lines per inch or per centimeter written on the grating by manufacturer. If N is the number of lines per inch, then the grating element is given as E plus D is equal to 2.54 upon N. So what is the meaning of this? Let me explain it with the help of a simple diagram. Suppose you have this grating, a plane transmission grating, right? And you will get a similar type of grating in your lab also. Now in this plane transmission grating, if you want to study the diffraction of white light, which is your visible light, which you can see through your eyes. So in order to study the diffraction pattern of that visible light or white light, the grating which we are using, that grating is having 15,000 lines per inch. So suppose you have this particular grating, and in this grating, there are capital N number of lines. So these lines which are drawn over this grating, let the number of those lines is capital N. So the space where you will draw the light will not pass through that particular point, and the space between the two lines, that will act as the transparent part, means it will act as E. So this is E because the spacing between the two successive lines, from that spacing light can pass, so it will act as a slit, and the bit of the line, that will act as the spacing between two successive slits. So this will act as D. Clear? So since you are having this grating, and let this grating is of 1 inch, 1 inch means 2.54 centimeter. So you can see in this 2.54 centimeter, n number of lines are drawn, means this E will be the, so total that bit is 1 inch, but in that 1 inch you are getting that E n times, as well as you are getting that D n times. So I can say that this n times E plus n times D, that total will be equal to 1 inch, and you know that 1 inch is approximately 2.54 centimeter. So from here, this grating element, what will be the grating element? It will be your 2.54 upon n. So for the plane transmission grating, which is used to get the diffraction pattern for white light, a grating will be provided to you which is having 15,000 lines in 1 inch. So if there are 15,000 lines in 1 inch, then this n will be equal to 15,000. So the grating element in that particular case will be 2.54 upon 15,000. So I hope you are getting that how to find this grating element, right? So this is again another application of this, that how you will find this grating element. Then determination of theta, that how you are going to find this angle of diffraction. So the grating is mounted in spectrometer in place of a prism such that the light falls normally on it. The various adjustments are made in the telescope to focus the grating spectra. The telescope is rotated to the right of the direct image to the slit. The crosswire is set on first order spectra and vernier readings are noted. Now the telescope is rotated to the left. So what is the meaning of this? Suppose you are getting, you are having a white light source and you want to find the angle of diffraction for different colors. So if this is the position of your light source, then at this particular position of telescope, this angle of diffraction will be 0 degree. So at this point you will get only white slit, because all the colors will mix here, angle of diffraction is 0, you will get a white light or white slit here. But when you will move towards left or towards right, then you will get that spectrum, you will get different colors, and you know which color will be observed first? The color which is having minimum wavelength. So violet, that will be the first line which you are going to observe, and if you will move towards the right hand side, again you are going to get that color which is having minimum wavelength. So you will get this violet color here. Then next will be the different colors of that spectrum: violet, indigo, green, yellow, orange, red. So in this way you are going to get that spectrum. If you want to find the angle of diffraction for this particular color, then what you have to do, you have to set your telescope, the crosswire of that telescope for this particular color, and then note down the readings of main scale and vernier scale. And then on the right hand side, again observe that particular color for the first order, and for that color find the main scale or main scale as well as vernier scale reading. The difference between these two readings, that will be your twice of theta for this particular color. Means this will represent the twice of angle of diffraction of a violet color. Suppose you are having this red color for the first order which is observed at this particular position. So what you have to do, you have to find the angle of diffraction here. You have to find this reading of red color from left, as well as you have to find this reading of red color from right, and the difference of these two readings, that will be equal to twice of theta for red color. So in this way you are going to find the angle of diffraction for different colors, and once the angle of diffraction is known, you will substitute it here and you will get the wavelength of that particular color. So this is the method to find the wavelength of different colors in a plane transmission grating, right? Now the next topic is dispersive power of a grating. So in order to understand that what is this dispersive power of a grating, so first I am writing your grating equation, the famous equation which you are using again and again in a plane transmission grating. Equation is E plus D sine theta is equal to n lambda. So if you will observe this equation carefully, then you can see that if the grating is fixed, means that this E plus D is fixed. So if E plus D is fixed, then for a particular order, means if this n is also fixed, means I am taking only first order spectra, then n will be 1. If I am taking second order spectra, then n will be 2. So for a particular order, for a particular grating, you can see this theta, that will change with wavelength, right? For different value of wavelength, theta will be different. So that rate of change of angle of diffraction, that how this theta will change with wavelength. So that rate of change of angle of diffraction with the change in wavelength, that is known as dispersive power of a grating. I hope this point is clear. You can see from this grating equation that once the grating is fixed, means that grating element E plus D is fixed. And if you have decided that you are taking observations for first order or for second order or for third order, then N is also fixed. It means this angle of diffraction that directly depends upon wavelength. So that rate of change of angle of diffraction with the change in wavelength, that is known as dispersive, that how the light disperse, how the those angles, angle of diffractions will change with the wavelength. That rate of change of angle of diffraction with the change in wavelength, that termed as dispersive power of a grating. So this d theta by d lambda, that is known as dispersive power of a grating. Now you have this grating equation, and using this grating equation you can simply find this dispersive power. So what you have to do, you have to differentiate this grating equation with respect to wavelength. So E plus D sin theta is equal to L lambda, that is your grating equation. Just differentiate it with respect to wavelength. So if you will differentiate it with respect to wavelength, you will get E plus D sin cos theta into d theta by d lambda is equal to N, because you are differentiating with wavelength. So what will be your dispersive power? Dispersive power will be simply from this expression, it will be equal to N upon E plus D cos theta, right? This is the expression for dispersive power of a grating. D theta by d lambda is N upon E plus D cos theta. And you also know from grating equation that E plus D sin theta is equal to N lambda. Clear? So this is grating equation. From this grating equation, if you want to find cos for sin theta, it will be equal to L lambda upon E plus D. So from here, if you want to write an expression for cos theta, what will be that? It will be under root 1 minus sin square theta. You know what is sin theta here? That is L lambda upon E plus D, right? So if you will substitute it here, they have written cos theta as under root 1 minus sin square theta. And you can substitute the value of sin theta as L lambda upon E plus D. So this is the formula for dispersive power of a grating. So I hope the meaning of dispersive power is clear. Means that rate of change of angle of diffraction with the change in wavelength, that is known as dispersive power of a grating. That how the angle of diffraction that changes with the change in wavelength, right? So the equation 2, this particular equation, that gives the dispersive power of a grating, and you are having following conclusion from this. The first one, the dispersive power is directly proportional to the order of spectrum. You can see here that d theta by d lambda, it directly depends upon N. Means if you have for a particular light source, if you have first order spectra and second order spectra, then the dispersive power that directly depends upon the order. Means the colors of first order, they will disperse less, whereas the dispersion for the higher orders, that will be more. Means d theta by d lambda, that directly depends upon N. So that is the first conclusion. Second one, the dispersive power is inversely proportional to grating element. You can see here that this d theta by d lambda, that inversely depends upon E plus D. So smaller the value of d theta by d lambda, greater will be the dispersive power. The third one, the dispersive power is inversely proportional to cos theta. So this you can see from there that dispersive power is inversely proportional to cos theta. Hence, for large value of theta, the dispersive power is higher. So these are the results which we can draw from the dispersive power of a plane transmission grating, right? Now the next topic which we are going to take, that is resolving power and the resolution limit of optical instruments. So basically the resolving power, we have to study here the resolving power of a grating. But before going into detail of resolving power of a grating, first we have to understand that what is the meaning of resolving power. So basically the resolving power of an instrument is the ability of an optical instrument to distinguish or resolve two closely spaced objects. You can understand it like this. As you know, in order to observe the distant stars, you always require a telescope. If you are seeing the clear sky with your naked eyes, then you can see stars on the sky. But if there are two stars which are very close to each other, and if their wavelength, the wavelength of those stars, the color which they are giving us, if that wavelength of those colors is very close to each other, then through our naked eyes we cannot distinguish, we cannot differentiate between those stars. So to see that sky or to see those stars clearly, we always require an optical instrument which is known as telescope. So the ability of that telescope, the ability of an optical instrument to differentiate or to resolve between two closely spaced objects, that is known as resolving power of a instrument. I hope this is clear. You have microscope in your biology lab, and you know what is the use of a microscope. That microscope that is used to see the tiny or smaller objects which are close to each other. So if you want to see those microscopic objects, then through naked eyes you cannot see those objects. So if you want to see those objects clearly, then you require that instrument which is known as microscope there. And if we are talking about optical instruments, then suppose we are having a telescope and you want to observe stars through that telescope. So the ability of that telescope or that optical instrument to resolve between two closely spaced objects, that is known as resolving power. And you have one more term here which is known as resolution limit, or it is also known as limit of resolution. The limit of resolution of an optical instrument, the limit of resolution of an optical instrument is defined as the smallest angle subtended at the objective by two objects which can be seen just as separate. So the limit of resolution of an optical instrument is known as, that is the smallest angle subtended at its objective by two objects which can be seen as separate. Lesser the limit of resolution of the instrument, greater will be its resolving power, because resolving power is inversely proportional to limit of resolution. So lesser the limit of resolution, greater will be the resolving power of that instrument, right? So this is about the meaning of resolving power and limit of resolution. So the topic which is a topic of next discussion, that topic is that what is the resolving power of a grating, and what is the criteria under which you can resolve with the help of an optical instrument or with the help of a grating. So the criteria under which you can differentiate between two point objects or between the diffraction patterns of two sources, that criteria is known as Rayleigh criteria of resolution. So the topic for next discussion, for next lecture, is the Rayleigh criteria of resolution. So we will try to understand that what is the criteria which if it is fulfilled by a optical instrument, we can differentiate between two sources or two different diffraction patterns, and using that criteria we will derive an expression for resolving power of a grating. So that is our last lecture in this chapter of diffraction. So in next lecture we will discuss about this Rayleigh criteria of resolution and the resolving power of a grating. So that's all for today. Thank you so much.